there's
Oh, I know, that's right, yep. So remember we were talking about these, this Rosslyn mean opacity. Can't do that with the line opacity because there's just a zillion speckle lines. There's no real way to average that, but we have this sort of average opacity. And this is a plot of the Rosslyn mean opacity as a function of temperature. So notice we've got log base 10 of the temperature in Kelvin along the bottom here, all the way from 10,000 to a billion Kelvin, seems excessive. And then the logarithm base 10 of kappa in square meters per kilogram, square meters of cross section per kilogram of stellar material along the y-axis here. And it's very complicated, as you can see, but this is for a composition of 70% hydrogen, 28% helium, 2% metals. What do we call hydrogen? What letter do we use to mean the hydrogen mass fraction? Capital X, right? Capital X, and helium, and everything else. Metals, as astronomers say, right? So this is X equals 0.7, Y equals 0.28, Z equals 0.02 is this composition right here. Alrighty. And then these are for, did I indicate that on here? These are for different densities, I think. I'm trying to remember, like the -6, -4, -2, 0. Those are densities, if I recall correctly, densities in kilograms per cubic meter. So you get a different curve for different densities. So, I've got labeled on here, we'll write it on the board as well. So, 1 here is showing that at low temperature, the free opacity, so notice the way these things go, is that they rise for a while, and then it reaches a maximum at some temperature and then starts to fall. So we want to explain in general terms why that happens. At low temperatures, the free opacity is small because very few atoms are ionized, and the bound free opacity is small since photons cannot cause ionization. So free opacity is due to what process? What's happening there? Free refers to what? What does the free mean? Electrons are not bound to atoms. So this is opacity due to electrons that are not bound to atoms, right? Free means it starts not bound, it ends not bound. So this is when you've got an electron in the presence of an ion can absorb a photon and increase its energy as a result of that. The ion needs to be there in order to conserve momentum as well as energy. So free opacity is going to be small at low temperatures because it's not hot enough to produce significant ionization. If atoms are not ionized, there are not free electrons, therefore there's very little free opacity. The bound free opacity, what does that refer to? Bound free means it starts bound, ends free. So what's another name for that process of going from bound to free? It's ionization, right? So that's the opacity due to ionization, where a photon with enough energy comes along and strips an electron off of an atom. So the bound free opacity is small here just because at low temperatures, typically you need like ultraviolet energy photons at least in order to ionize things, maybe even more than that. And at low temperatures, there's very few photons that have enough energy to ionize anything. So at low temperatures, the free and bound free opacities are small because everything is pretty much neutral and the photons don't have enough energy to change neutral things into ionized things, is what it comes down to. So that's that end of the scale there. So let's write that up. At low temperatures, low T, the opacity is low. By the way, you should also put, so that you're prompted, have a look at figure 9.10. liquid slide version. At low opacity, at low temperatures, the opacity is low because few atoms are ionized. So kappa free, the bound free, the free opacity is small. And few photons have enough energy to cause ionizations. So I should put a bar on that. It's the mean opacity we're talking about. The Roslin mean free opacity is small. So the Roslin mean bound free in the second case is also small. But the opacity is very steeply rising with temperature to here because the number of free electrons, the per cubic meter, N sub E, is rising due to, as you increase the temperature, this is 10,000 Kelvin, right? That's where in a star hydrogen becomes ionized, right? Remember that's about the transition temperature. So as you cross the 10,000 Kelvin threshold, you start getting a lot more ionization of hydrogen and helium, which are the most abundant elements there. And so that's going to increase those two opacities because you're going to both get, well, it's essentially mostly the free, I think, because you're getting a lot more electrons around, is what it comes down to. But you'd also get some increase because you're getting more energetic photons as well. You get some increase in the bound free opacity. So the initial steep rise with increasing temperature corresponds to the increase in N sub E due to the ionization of hydrogen and helium. So once you get a good level of ionization, we start to get Premier's opacity law coming in. So in other words, if you're in between about 10,000 and 40,000 Kelvin, then H2 and He2 predominate. What does the 2 mean, the Roman numeral 2? Yeah, one electron has been removed because, of course, for astronomers, we use a Roman numeral, which is one more than the number of electrons that has been removed. So in that regime, both the free and bound free opacities are roughly proportional to temperature over T to the 3/5 power. In other words, it's falling with temperature. As T goes up, the temperature goes down. There's also a proportionality to rho, which is why there's a bunch of curves here for different rhos. As rho increases, the opacity increases. For a given rho, as T increases, the opacity decreases. increases. So there's a family of curves, one for each row, and in this regime, each one is going like 1 over t to the 3.5 power, roughly speaking. So on a log plot, that plot is a straight line with a slope of minus 3.5. So we've got these downwards, almost straight line slopes that are looking like Cramer's opacity. So, and I should say, this plot is done with detailed calculations of the opacity. So we're seeing that detailed calculations give roughly what Cramer's law says should happen. So the next thing we write is above around 10,000 Kelvin, H is mostly H2. And helium is mostly helium-2 below 40,000 Kelvin. Because remember, 40,000 Kelvin is where helium starts to become doubly ionized. So the curve peaks. We've ionized everything. We're not increasing N-sub-E anymore. Already at full, well, I shouldn't say full ionization, that means everything is stripped off, so that's not quite what I mean. But in other words, we are already at the point of having stripped off all the first electrons, so to speak. We're already at the point of having removed one electron from both H and E. So Ne is not increasing. Oh, I already said that because Ne is no longer increasing, so that was the explanation. From both H and E. Close parentheses. Back the camera out so that our guest can be seeing the rest of the blackboard too, and I can start writing over there. Okay. Past the peak, the curve for each density curves are labeled with log 10 rho in kilograms per cubic meter. That's what the -4, -2, 0, 2, 4, all that means. So the curve for each density falls off following the Cramer's law. Following, hopefully, a Cramer's law. Which says kappa bar looks like rho t to the -3.5. So computer programs have to have detailed tables that can look up the mean opacity given the temperature, density, composition. If you're making a detailed computer stellar model, your model needs to be able to look up what the opacity is as a function of temperature, density, and composition. Okay, any questions? Now another feature is, notice that at around 40,000 Kelvin, there's a little whoop, 4 here, a bump there, and a bump there, and a bump there. All the curves have a little bump at about 40,000 Kelvin. That's coming in because Ne jumps again when you doubly ionize the helium. You get another jump in the number of free electrons, which increases the free opacity. The jump on each curve at about T equals 40,000 Kelvin is due to the increase in kappa bar free when helium-2 transitions to helium-3. Remove that extra remaining electron from the heliums, you get more Ne, more electrons, more free electrons. More free electrons, Ne goes up. And then eventually every curve flattens out to a nearly constant value, and that's because of the fact that eventually electron scattering dominates. Once the temperature gets big enough, the Cromer's opacity law, that contribution becomes negligible, and so then the electron scattering dominates. And remember that, or be reminded that electron scattering is independent of temperature and density. So in other words, deep in a star's interior, where the temperature is very high, electron scattering is the main source of opacity. So like in the sun's core, much of the radiative zone, electron scattering dominates the opacity. The main thing that's happening is photons keep bumping off of electrons. So electron scattering dominates at high temperatures. So all the curves approach the same limit. All the curves for different densities approach the same limit. Since kappa bar for electron scattering, remember that was 0.02 times 1 plus x square meters per kilogram. they'll approach a constant opacity deep down where the temperature is very high. So much of a stellar interior, electron scattering dominates the opacity. It's the main thing giving photons a hard time getting out. Yes?
What is X in this situation?
Capital X, it's the hydrogen mass fraction. It's the hydrogen mass fraction. Remember, capital X is the hydrogen mass fraction, capital Y is the helium mass fraction, capital Z is the metals mass fraction. So, this illustrates that photons trying to get out of a star after being generated by fusion in the core are basically drunken sailors, staggering their way out towards the surface. As we will see, estimates can vary, but energy takes something like 100,000 to 1 million years or so to go from being generated in the core to finally making it to the surface. Neutrinos stream right out of the sun. They travel at almost the speed of light, and they hardly interact with anything. So you create a neutrino by a nuclear reaction in the sun's core. It gets out within about 2 seconds, because that's how long it takes to travel the sun's radius at about the speed of light. Photons, on the other hand, take something like 100,000 million years. So if you think about it, essentially what that means is, ignoring the fact that photons sometimes get absorbed, and so it's not really the same photon, but if you pretend it's the same photon the whole way, it has to travel something like 100,000 to 1 million light years to make it all the way out of the sun. So it's as though it travels the length of the Milky Way galaxy, bumping around before it finally gets out of the sun. So this illustration doesn't even come close to showing how many zigs and zags it takes. It's just to show the general kind of idea. If it doesn't get a straight shot. So it takes a long time to make it out. So a process like this is called a random walk, and we will derive an expression for how many steps it takes to go a given distance in a random walk. It's actually very important because it shows up over and over again in physics and astrophysics. The simplest illustration of a random walk would be, here I am on some square, and let's say I started in the middle of the room. I think I'm still on it. I started in the middle of the room, and I'm only going to move in one dimension. So I'm going to flip a coin, and if the coin is heads, I take a step forward, and if the coin is tails, I take a step backwards. Now, if I always took a step forward, it would take me, or backwards, it would take me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, about 14 steps to hit the back. Maybe I'm on the same square I started on, I don't know. Anyway, what if instead I do it with the coin flips? Well, then it's going to take me longer because I might go heads, heads, tails, heads, tails, 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 heads, tails, heads, heads, right? So it's going to take a while. Eventually, Eventually there will be a point where I smack into the wall, because slowly but surely you do, because of the random statistical nature of the coin tosses, you do end up drifting away from where you started. But it takes a lot more steps if you're guiding yourself with coin flips, as opposed to if you just take a step forward or a step backwards every time. So let's derive an expression for how many steps it takes. And what we will discover is that, roughly speaking, the number of steps you take on average, the number of steps you take on average to randomly walk a given number of steps in one direction or the other is the square of the number of steps that represents your progress. In other words, on average, for me to go 10 steps forward or 10 steps backward, I would need about 100 coin flips to do that, to have wandered about 10 steps forward or 10 steps backward. To go 100 steps forward or back, on average, it would take 1,000 coin flips to do that. So let's derive that result. So I'm going to head this as gradient of transfer, because what we're going to do is ultimately, in this section, develop what's called the transfer equation that describes the propagation of light through an opaque medium. But in particular, we're going to start with a random walk, talking about a random walk. So let's do it not just in one dimension. So you don't have to duplicate what I'm doing in exact detail. You just have to do something which is similar to what I'm doing here, which is, you imagine starting at some location, ending at some location. There's D, the total displacement from the start to the end. And there's a bunch of random steps along the way. And we're going to label the random steps vector L1, vector L2, etc. Vector L sub capital N is the last step. So what we'll do is to keep things simple, because something making a random walk, like a photon, it's not going the same step length every time. So what we'll do is simplify and just say, let's imagine every step is of length equal to the mean free path, the average distance that it manages to go between collisions, between redirections. Imagine a random walk with each step in a random direction. But to keep things simple, we'll say each step is of length equal to the mean free path. Each step is of length L equals mean free path. total distance d, not the vector, just the distance d traveled after n steps is, so let you catch up with that. Okay, no, not quite ready yet. So d squared is d dot d, because any vector dot itself is the square of its magnitude, right? d cosine 0 degrees is d squared. So d squared is d dot d. But d, the total displacement, is just the vector sum of all the individual displacements. So it's the sum over I of all the li's dotted with the sum over j of all the lj's. And I've used two different subscripts because of the fact that I don't want to confuse steps with one another, so to speak. In other words, the subscript in a sum is always a dummy index, right? In other words, the sum, actually I'll be more explicit, the sum from I equals 1 to capital N, the sum from j equals 1 to capital N. So you guys see, those are really the same thing. The sum from I to equals 1 to n, the sum from j equals 1 to n. They're the same thing because each of them means L1 plus L2 plus L3 plus L4 dot dot plus L sub n. So both of those things mean the same. But if you're going to dot them with one another, you need to use a different subscript for each one because you need a double sum, not a single sum when you do the dot product. And so if you had a single subscript, you wouldn't be able to do that. You wouldn't be able to distinguish L3 dot L5 if you were using the same sum index for both sums. So this will be, or you can break this into the sum of the terms where the two subscripts are equal and a sum where the two subscripts are not equal to one another. So in other words, you can say that this is the sum over I equals j of Li dot Lj plus the sum for when I is not equal to j of Li dot Lj. Just separating it into the dot products when it's the same pair of vectors and the dot products when it's not the same pair of vectors for each of the steps. So how many terms are there where I and j are equal to one another? If you're summing from 1 to n, how many terms are there when I and j are equal to one another? There are n such terms, right? I mean, if you want to be explicit, if I had L1 plus L2 plus L3 dotted into L1 plus L2 plus L3, then there would be 3 terms of the form L1 dot L1, L2 dot L2, L3 dot L3, plus other terms where they're not equal to one another. So this will be n terms, and each one of them, because we're assuming all the steps are the same length, each one of them has length each one of them has magnitude L squared. In other words, Li dot Li is L squared because all the steps are the same length. So every Li dot Li is L squared, the length of each step. So this is number of steps times L squared, that term. And for the other terms, we'll say that theta ij is the angle between Li and Lj. So for the other one, that'll be, with that notation, Li dot Lj is the magnitude of Li times the magnitude of Lj. Well, that's all L, so it would be L times L. L squared times the cosine of the angle between them, because the dot product is magnitude of the first times the magnitude of the second times cosine of the angle between them. So the second term is L squared times the sum over all the terms where I and j are not equal of cosine theta ij. As the number of steps becomes very large, as you start to have a very large number of steps, as n goes to infinity, this term just gets bigger and bigger and bigger and bigger. It's proportional to n. This wanders around. It won't be 0, but it'll be very small compared to n, because this is a mix of both positive and negative terms. Whereas all these terms are positive. This is just one big number, n times L squared. This is a mix of both positive and negative terms, so there will be a lot of cancellation. So as n goes to infinity, the sum of the cosines, we can say, meanders around. Doesn't know what it wants in life.
Just like me.
There you go. Since some terms are negative and some are positive. So we can neglect the second term in comparison with the first as long as n is very big. Then what we find is the net distance you travel is approximately equal to the length of one step times the square root of the number of steps, because this is saying then, if we throw that term away, d is approximately nl squared, d squared is approximately nl squared, so d is approximately the length of one step times the square root of the number of steps. In words, the total displacement increases as the square root of the number of steps. On average, any given random walk, it's a random walk, but on average, as the square root of the number of steps. Each of these tiles is a foot long. So one step here is 1 foot. So if I'm random walking, tossing the coin, we've said it already, but again, I want to be sure you're on board. After 100 coin flips, about how far should I be from where I started, typically? This would be averaging many, many random walks together. I should be about 10 steps, or in other words, how many feet? 10 feet away, right? In other words, length of one step, a foot in this case, times the square root of the number of steps. After 1,000,000 steps, I should be about how many feet away from where I started? What's the square root of 1,000,000? What is 1,000,000 as a power? 10 to the... So what's the square root of that? 10 to the third, which is a 1,000. So after 1,000,000 coin flips, I'll be about 1,000 feet away, right? So it only took me 999,000 more steps than it would have taken if I had just walked straight, right? So I'm pretty sure Einstein was a problem. If I didn't, what's the matter with me? You figure out then how long does it take photons to get out of the sun? The idea would be, well, what's the mean free path? About how far does a photon travel in one step? How many steps of that length would it take it to get out of the sun if you assume the mean free path stayed constant? How many steps would that take if it just took a straight step each time? So the number of steps it'll actually take on average is the square of that, which is why it takes photons so long to get out of the sun. If it would normally take, if you did a straight shot, if it would take 10 to the 10 steps, it's actually going to take 10 to the 20th steps to get out, etc. And so that's why it takes photons so long to get out of the sun, because it takes so many freaking many steps to get out, because the mean free path is such a tiny fraction of the total steps of the sun. Break time. Break time.